We're going to begin our series work on testing whether series converge or diverge by talking about a really common series that we see a lot called the geometric series. Now, we already talked about geometric sequences, so it shouldn't be any surprise that when the nth term of a geometric sequence looks like that, when we add the terms together, we have a geometric series. So the nth term is going to be some fraction raised to the power of n. We'll see the formal form for a geometric series in a bit, but it's going to be some real number value raised to an exponent. It's going to look like an exponential function if it were in terms of x instead of in terms of n. And each one of these terms has something we call the common ratio. It's denoted by lowercase r. So each term is obtained from the preceding number, from the preceding term, by multiplying by the same number r. And that's what a geometric series looks like. If we were asked to find the common ratio r, which we usually are not, we're usually just given the nth term, and all we have to do is recognize the fact that it is a geometric sequence. So let's say we wanted to find r. We could take any two terms in the sequence, and we're going to divide the rightmost term by the term to the left of it. So let's say I took these first two terms, and this is a negative, so we would need to make sure we have the negative. Remember, if you are dividing by a fraction, you get to flip the bottom fraction. So this says the common ratio for the first series is -1/5. We could check that by taking the next term and dividing it by the term just to the left of it. And so mathematically, we're going to get this, which again is -1/5, which is the common ratio. So let's find the common ratio here. We'll use the first two terms. That will be 4/3 divided by 2/3, which would be 3/2. So here it appears the common ratio is 2. We would check our work just by checking the next two terms. And I'm not writing a fraction over fraction. I'm going right ahead to this second step like we did here. And so that's 8/4. And sure enough, the common ratio is 2. So the common ratio is not difficult to find, but it is helpful to us if we will recognize the general form for a geometric series. And here it is right here. The nth term is going to be of the form a, which is the first term in the series, times r, which is the common ratio, we just saw that, raised to the n-1. And this n-1 is really important. It needs to be in that form for us to be able to do some things that we need to do with the geometric series. For instance, for us to find the sum of a geometric series. We used this one in the first example. We found the common ratio of this one here. And so if we're going to write those in the form of a times r to the n-1, we would need to find the common ratio, which would look like this. And so clearly we can see there's the common ratio. The first term, always, the first term in a geometric series is a. So we can see here, there's a. So this is in the form a times r to the n-1. And if we started at n=1 and only started with the nth term, and we wanted to generate the terms of this series, let's just double check that it works backwards. So when n=1, we have 1/2 times 1/2 to the 1-1 plus 1/2 times 1/2 to the 2-1. I'm starting with n=1, and everywhere there's an n in my nth term, I'm just iterating through the integers. This one would be 3-1, and we would keep going. So 1 - 1 is 0, so the first term would be 1/2. The second term would be 1/2 times 1/2, or 1/4. The third term would be 1/2 times 1/2 quantity squared, or 1/8. Then we can come back over here and see, sure enough, that is generating our geometric series for us. You can take the time to do these if you want to, but we would find the common ratio just as we did the others. That's a negative. 5/3, that's going to reduce to 4/5, and sure enough, there's R. Here is A. If we were to generate the terms, we would have 3/5 times negative 4/5. This tells me where to start with n. So I would start with n equal 1. 1 minus 1 is 0. That's how come I'm just going to get 3/5 for my first term. So it turns out, if you can see this, this is a times r to the 0, or we might just call that a. The second term is a times r to the 1. The third term is a times r squared. And that's actually how this general geometric series will wind up looking. A times r times a times r squared times a times r cubed, and so forth. And in that form, it's easy for us to recognize A, and it's easy for us to recognize R. And as I said, when we talk about the sum of a geometric series, recognizing A and recognizing R is super important. Now, we did this on the last slide, so I won't take time to do it. We did indeed find that the common ratio was 2. Here is A. The first term is always A. We would have 2/3 times 2. We start at n equal 1. The 1 minus 1 plus 2/3 times 2 to the 2 minus 1. And we would keep going. And so you would see that that would generate those next terms in the series. So geometric series are really easy for us to generate from the nth term. They're super easy to recognize because it feels like or looks like an exponential function if it were in terms of x. So recognizing a geometric series is important because it's one of the very few series where we can actually find the exact sum. Lots and lots of times on our series, the best that we're going to hope to do is to be able to determine whether it converges or diverges, not what its exact sum is. So being able to find the exact sum of a series is going to be pretty powerful for a lot of tests that we're going to run. This is a great set of series and nth terms that we can use for comparisons and so forth, and you'll see that as we move through this work. So, the sum of a geometric series, if it converges, will always converge to the sum equals the first term over the quantity 1 minus the common ratio. It will converge, and this follows really closely. It's exactly the same. It follows from our geometric sequences. It turns out that what we learned for a geometric sequence to converge is the same thing that we need for a geometric series to converge. If we identify the common ratio R and the absolute value of that common ratio is less than 1, then our geometric series will converge. And if convergent, once we determine that it is convergent, it will always converge to that value. If, and that should be absolute value, make sure that goes in your notes as absolute value, or if R is less than -1 or greater than +1, then the series diverges. So it turns out being able to recognize the value of R tells us a lot about our geometric series. So let's look at some examples. Find the sum of the geometric series or state if the series is convergent. Well, these are the same series we saw a while ago, so all we have to do is recognize A, recognize R, determine whether the absolute value of R is less than 1, and state the geometric series converges. And if the geometric series converges, the sum will always be A over 1 minus R. This is 1/2 over 1/2 The sum of this series is 1. Let's do the same thing here. Remember, our nth term is always, if it's to this power, always in the form of a times r to the n minus 1. So we recognize what a is. We recognize what r is. We show the AP reader that we recognize the absolute value of r is less than 1. Identify it as a geometric series. And state to the AP reader you recognize when the absolute value converges. When the absolute value of r is less than 1, the series converges. The sum is a over 1 minus r. That's what the sum would be. So 3/5 over, this is 5/5, that would be 9/5. That sum would be 1/3. So super easy. Let's do this one. A is 2/3. Again, I'm looking for my nth term to be in the form of a times r to the n minus 1, and it clearly looks like it is. R here is 2, but the absolute value of 2 is not less than 1. So I would show the AP reader that this geometric series diverges. And if a series diverges, it has no sum. So geometric series could not be easier. The only wild card or kicker here is if you find yourself with your nth term in an incorrect form. You're going to have to work on it, and you're going to have to put it in the correct form before you can determine whether it converges or diverges. You need it in the form of the first term is a, the second term is a times r, the third term is a times r squared. A lot of students would look at this and say, okay, well, a is 7, r is 1/8, absolute value of r is less than 1, and therefore the sum would be 7 over 1 minus 1/8. Which is not true. The sum is not going to equal that because it has to be in the form of a times r to the n minus 1. So my suggestion is generate the first few terms. Force those terms to look like a plus a times r, where we are to degree 1, plus a times r squared, where we are to degree 2, which is what we've done here. You can clearly see here's a times r to degree 1, a times r squared, and that makes it easier to have it in the correct form, a times r to the n minus 1. All right, so here a is 7/8, r is still 1/8, but you can see that the sum would wind up very different from what we were originally going to get when it was in the wrong form. So if it's in the wrong form, you must put it in the correct form for a geometric series. And again, you must show that you recognize that it is a convergent geometric series before you go about finding the sum. So this is 7/8 over 7/8. That has a sum of 1. All right, so there's geometric series. Really straightforward. You have to recognize r, recognize a. If it's convergent and you're asked to find the sum, it's a over the quantity 1 minus r. Geometric series are really powerful for us, so make sure that you are really comfortable working with them. There's just this one video for the lesson. Come to class next time, and we'll do some homework problems and get really familiar with geometric series.